MDM4U 7.2 binomial distributions. So, a binomial random variable has the following characteristics. An experiment is being conducted with a set number of trials, so there's a total number of trials. The outcome of each trial is either considered a success or failure. And trials are independent. The chances of success or failure are the same in each trial. So it's given by the following formula. Later on, we're going to give an investigation as to why do we have this n choose x in front of p to the power x times q to the n minus x. What we'll say is the following. X is the number of successful trials, n is the total number of trials, p is the probability of success, and q is the probability of failure. You may see that this formula has q expressed as 1 minus p to minimize the number of variables used to be able to express this equation. Next, the expected value of a binomial random variable is given by n times p, where n is the number of trials, p is the probability of success. I will be including an additional video to demonstrate how do we go from the sum of x times the probability of x to such a simple formula. It's not easy, but super interesting. So that'll be included as a bonus video in the 7.2 content folder. Now, in Chapter 6, we did the following, Introduction to Probability. We looked at specific values of a random variable. But we'll later learn that a distribution is about observing all of the possible outcomes of a random variable. So, a die is rolled 10 times. What is the probability that you will roll a 6 exactly 3 times? So there's 10 trials, and we're looking for 3 successes. So, we're going to apply the guess method. The given information, there's 10 trials. The probability of success is 1/6. The probability of failure is then 5 out of 6. X, the random variable, we're interested in when is it exactly 3 out of the 10 trials. And what is unknown in the guess method is the probability when x is equal to 3. So here's our equation, and we're going to substitute in these values and then solve. So notice these components, and I'm just going to go over this briefly and then in more depth later. 3 choose 3. This is representing the number of ways in which we could have 3. Oh, that's an error. That should be 10 because there are 10 trials. 10 choose 3 because this is how many different ways we can have 3 successful trials in 10 total trials. 1/6 to the power 3 represents the successful factors, and 5/6 to the power 7 represents the failures. So 3 plus 7 is equal to 10, the total number, 3 of which are success, 7 of which are failure, and this is our final value. And to apply the expected number, the expected value formula to this problem, what is the expected number of times that you would expect to roll a 6 in 10 trials? N is 10. There's 10 trials. The probability of rolling a 6 is 1 out of 6 in each trial. So our expected value formula specific to a binomial probability random variable is n times p, where we have 10 times 1/6, which is approximately 1.6 repeated. Now, let's look at this example. Online, we've been doing the following. A student completely guesses on a 5-question multiple choice test where each question has the options A, B, C, or D for each question. So, create a probability distribution table for the number of correct questions answered and illustrate the distribution of the number of correct questions answered. So here, this is a probability distribution table because it illustrates the outcomes, or it calculates the outcomes of each value of the random variable. If there's 5 trials, 5 questions, just like our multiple choice test, you could have either 0, 1, 2, 3, 4, or 5 correct answers. And if you are completely guessing, that means that each and every single trial you have a 25% chance of successfully guessing and a 75% chance of incorrectly guessing the answer. So this is the binomial probability formula customized for this specific scenario. That being said, this is the graph of the probability distribution, and it shows you that typically we would expect somewhere around 1 correct answer. Okay, so that being said, we're going to look at a further investigation. let's see, why do we have that combination out in front? And we're going to suppose a scenario where the chances of winning in a game is 60% every single time. And for one case, it's not really interesting. I'm going to skip to the most important component. One game of 60% chance winning, 40% chance of losing looks like this. And our random variable is either going to be equal to 0 wins in one trial or 1 win in one trial. Next, we don't really need to go into this because it's not really relevant yet. When we look at 2 trials, we can see that we could possibly, if we wanted to have 0 wins, we would just have a loss and a loss. And it's not really necessary to use this formula yet. And if we wanted 2 wins, we could have win-win. But if we wanted exactly 1 win, we could have win-loss or loss-win. So we know that we can multiply the branches of our path to get to a specific result because of the fundamental counting principle. But notice this, win-loss or loss-win will produce 1 win. So we can say that that's 2 times the first term, 0.6 times 0.4, because whether we multiply 0.6 times 0.4 or 0.4 times 0.6, they're the same. So we can multiply 2 times that value. Still not really relevant enough to show why that combination is important, but as it gets more complex, we're talking about 3 trials. And if I ask you, for example, the number of ways in which you can have 1 win, well, we could have win, loss, 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 win, loss, or loss, loss, win. And the calculation for this is a little bit, we try to fit that all in one line. All right, so same thing with this here. There are 3 different scenarios where that can happen. So we have to think of all the different ways in which that can occur, additive counting principle, and then calculate them individually, which is a multiplicative counting principle, looking at those outcomes. So win, win, loss, win, or this last one should be, it's loss, win, win. So now we're seeing that this factor out front represents the number of ways in which we can have that result. And this right here is an abbreviation to express that we really just have 2 wins and 1 loss. They can happen in different orders, 3 different orders to be exact.